All right, welcome back. Today, we are diving deep, really deep, into the heart of matter itself. We're going to crack open the atom, figure out what's inside, and then we'll see how those tiny pieces come together to build, well, everything you see around you.
Just think about it for a second. Everything, the chair you're sitting on, the air you're breathing, it's all made of atoms. But for centuries, they were a total mystery. So how on earth did we figure out what's actually inside them? That question right there kicks off one of the greatest detective stories in science.
So our story really starts back in 1808 with a guy named John Dalton. He had this big idea that everything was made of these tiny, indivisible particles, like little solid balls. And honestly, that was a huge leap. But our modern view, it's completely different. We know now that atoms can be split, and get this, not all atoms of the same element are even identical. We'll get into that later with something called isotopes. So the real question is, how did we go from point A to point B?
Well, it really all came down to a series of incredible experiments. Scientists, one by one, started finding these little clues that the atom wasn't this solid, unbreakable thing Dalton thought it was. It was time to crack the case and crack open the atom.
Okay, let's look at the timeline. It really shows the key breakthroughs. We're talking about a wild 35-year period that just totally flipped our understanding of the atom on its head, piece by piece.
So the first big clue drops in 1897. A scientist named J.J. Thomson is messing around with these weird energy beams, cathode rays, and he finds something, a particle that's super, super tiny and has a negative charge. He calls it the electron, and boom, just like that, it's proven. Atoms have smaller parts. The old theory is officially broken. But, a discovery like that just leads to another question, right? If atoms have these negative little electrons in them, but atoms themselves are neutral, well, there has to be something positive inside to balance it all out. What was it, and where was it hiding?
And that brings us to the proton. Yep, the positive counterpart. Through more experiments with energy beams, scientists found this particle with a positive charge, the perfect opposite to the electron. But here's the kicker. It was way, way heavier. We're talking over 1,800 times more massive than an electron, a real heavyweight.
Okay, so now we've got two pieces of the puzzle, a heavy positive proton and a tiny negative electron. But how are they arranged inside the atom? To figure that out, in 1911, Ernest Rutherford came up with this genius experiment. The idea was actually pretty simple. He was going to shoot these tiny positive particles, alpha particles, at a ridiculously thin sheet of gold foil and just see what happened.
Now, what Rutherford saw was, well, it was completely bonkers. He thought most of the particles would just zip right through. And yeah, most of them did. But some of them got deflected, and a tiny, tiny fraction, like 1 in 20,000, bounced right back at him. He famously said it was like firing a cannonball at a piece of tissue paper and having it bounce back and hit you. Just unbelievable.
This is where Rutherford's genius really shines. From that completely unexpected result, he figured out two mind-blowing things. First, since most of the particles went straight through, the atom had to be mostly empty space. And second, for one of his positive alpha particles to bounce back so violently, it must have hit something super tiny, super dense, and also positively charged. He had discovered the nucleus.
So the picture is getting a lot clearer, right? But there was still one more puzzle to solve. When scientists did the math, the atom's total mass was always more than the mass of its protons. Something was missing. There had to be something else in that nucleus, something with mass but no charge.
And finally, in 1932, James Chadwick found it, the neutron. It's a neutral particle hanging out in the nucleus with the protons, and it has almost the exact same mass. And with that, the subatomic puzzle was complete.
So, now that we've found all the pieces, we can finally put them together and see the modern blueprint of the atom. This is how we picture it today.
And there it is, the whole shebang. You've got that dense little center, the nucleus, packed with positive protons and neutral neutrons. And then, zipping around that nucleus, you have the super lightweight negative electrons.
Let's break it down real simple. The protons, they give the atom its identity. They decide what element it is. They're positive. The electrons, they're negative, and they're the ones that get involved in all the action, the chemical reactions. And the neutrons, they just add mass. They're neutral. That's it. The way these three dance together defines, well, everything.
And this brings us back to that idea of isotopes. Remember how we said not all atoms of an element are identical? Look at hydrogen here. All three of these are hydrogen because they all have one proton. That's the rule. But you can see they have different numbers of neutrons. So they're all hydrogen, they all act like hydrogen, they just weigh a little different. That's what isotopes are.
Okay, great. So we know what an atom looks like. But here's the thing. Atoms almost never hang out by themselves. They're always interacting, bonding, making molecules. The big question is, why? What makes them do that?
You know, the answer is actually pretty simple. It's called the octet rule. And basically, it just means that atoms are happiest, or, most stable, when their outermost shell of electrons is full. For most atoms, that magic number is 8. It's like they're trying to collect a complete set of something. And that desire, that push to get a full outer shell, is the engine that drives almost all of chemistry.
So to get that full, stable outer shell, atoms basically have two main moves. They can either give an electron away or steal one from somebody else. Or they can decide to share electrons with another atom. And those two strategies give us our two main types of chemical bonds.
First up, we've got ionic bonds. This is the give and take strategy. It's a complete transfer of electrons from one atom to another. Then you've got covalent bonds. This is the sharing is caring strategy. Here, the atoms team up and agree to share their electrons. Let's look at how this plays out in the real world.
Let's take a look at good old table salt, sodium chloride. So, you've got sodium, and it has just one measly electron in its outer shell. It is dying to get rid of it to be stable. And then you have chlorine, which has 7. It's so close. It just needs one more to have a full set of 8. So it's a perfect match. Sodium just gives its electron to chlorine. Now sodium is positive, chlorine is negative. And zap! Opposites attract. They snap together, and you've got salt.
All right, now let's look at the sharing strategy with water. Oxygen needs 2 more electrons to be happy. Each hydrogen atom only needs 1. So a simple transfer isn't really going to work for everybody. Instead, they team up. The oxygen atom shares one of its electrons with one hydrogen and shares another electron with a second hydrogen. By sharing, everybody involved gets to feel like they have a full outer shell. It's a win-win, and that powerful teamwork creates the water molecule H2O.
And really, that's the whole game right there. Whether we're talking about the salt on your fries or the water in the ocean, it all boils down to this one simple thing. Atoms trying to get a full outer shell. This basic need to gain, lose, or share a couple of tiny electrons is what builds the entire complex, amazing world we live in.
So, when you think about it, we've come a crazy long way from Dalton's idea of a tiny, solid ball, right? We've cracked the atom open, we've met the players inside, and we've even figured out the basic rules of how they interact. But it really makes you wonder, doesn't it? What other secrets are these little building blocks still hiding?